Hey guys, my name is Adrienne and welcome to Organic Chemistry 1, part 9 of these recorded sessions. Today we'll be going over for most of y'all chapter 9 but in general alcohols, ethers, epoxides and hydride and alkyl ships. So here is our agenda and like I just mentioned, it's very straightforward. So we're going to be focusing on naming and the reactions that comes with these four topics. So as always, I'll have the topics, the titles up on each page reduced, so feel free to scroll to which topic you want to go into first. So with that being said, let's get started with alcohols. Okay, so alcohols. So now we're getting into the functional groups of alcohols and then ethers and then so on and so forth. So each of them have certain reactions, each of them have certain names. And this is important because once you start mixing them up, they you have to know which are the priorities. So alcohols are going to be prioritized over alkanes, alkenes, alkynes, right? Things like that. So let's go ahead with alcohols, and as the same with alkanes and alkenes, we're going to have classification, and it's pretty much the same as the hydrogen classification. So let's just go into that. So OH over here, H, one R group, H, and then keep adding on, right? So OH here, R, R, H, and then from here you can kind of tell like um, what the structure looks like. You can tell that this is much more hindered than this one, things like that. So we have primary, secondary, tertiary. Nothing too crazy. We've seen it before, right? We care about the carbon directly bonded to the oxygen, right? So as you can see, the more we go, and let me change the color just to, emphasize it a little bit more. The more we go this way, increasing steric hindrance, right? Hindrance, increasing hindrance, and then obviously the less hydrogen bonds we have, right? So, and I'm not even gonna point that out, but well, let's go ahead. So obviously there's gonna be less hydrogen bonds, which is important because um, you know, these could take into play like from the last video, we know we need hydrogen bonds for some reactions, right? We need to take away some hydrogen bonds or some hydrogens in general, like protons, things like that. So just a little bit tidbit. And now let's go to naming. So we know same rules apply, longest chain, things like that. And then here, there's actually two endings. IUPAC ending will consist of all, right? So butanol, propanol, things like that. And common ending would be, and then alcohol. So um, we'll see later when we start naming, we're going to be using both of these, IPAC and then common. So common literally just ends with alcohol. So you describe, a common molecule and just add alcohol, right? Nothing too crazy. And here's some common ones. OH. This one is called enol. And then this one, you'll see this a lot. This one a lot. Phenol. Phenol, right? So nothing too crazy. So with that being said, let's go jump straight to the reactions. And this is how I did my reactions. It's pretty similar to what you guys have in your books and stuff, but I kind of just condensed it into one um, kind of web, right? So reactions. So first we have reactions with that turns alcohols to alkyl halides. So first, let's start off with ROH, right? Our alcohol, and then we're gonna end up with 5. And that's kind of how I did mine. 5. So let's start with HCl, SOCl2, HBr, PBr3, and then HI, right? So obviously all of these are going to be Cl, replacing that OH with whatever the halogen is, right? So because it is alcohols to alkyl halides, so nothing too crazy, right? So you're just replacing that OH with whatever halogen there is. But this is where the fun stuff comes in. Certain reactions, again, we talked about substitution, elimination, SN1, SN2, E1, E2, things like that. So in this case, they're obviously substituting, right? So this one, HCl, goes through either SN1, SN2, right? So it's going to be a racemic mixture. So either one. But for SOCl2, it prefers SN2 only, right? So there's going to be a backside attack, things like that. This one, same thing, SN1, SN2. This one's just SN2, and then this one is SN1, SN2. So does that make sense? So if you see an HCl, you can attack from front side, back side. If you see SOCl2, that's going to be a backside attack, and you know that R is going to turn to S, or S is going to turn to an R, things like that, right? So this is what's important here, and a lot of students don't realize that, and just plug in Cl to everything or whatever, or Br, or you know iodine, but that's not the case because for HCl you can have two products, right? But for SOCl2 you're just going to have one product because it's just backside, right? So think about that. This is what's important, right? Okay. With that being said, let's go to the next set of reactions for alcohols, which is alcohol, which is going to let's see, substitution elimination specifically. So substitution elimination. Oh, elimination. Right. So this we can start off the same way. Um, but this time let's use a cyclic OH. And then I do the same thing. I do my arrows, right? There. And then H2SO4, or there's a couple options here. POCl3 and pyridine. And then this one, HX or SOCl2. Basically, this second part is the stuff we just talked about with to the alkyl halides, right? Or PBr3. This one, this one's a special one. So when you see this, a certain reaction should go through your head um, automatically. So this one, this is gonna eliminate it, right? This is the elimination part. So you either get this or you know this because we just eliminated the OH. For this one, we know we get an alkyl halide, so whatever halogen there is. Okay, and in this one, we go to this tosylate group, right? TS is tosylate, OTS, right? But this can go further, and this can go further. And what are you guys thinking? Right, they can again get either substituted or eliminated, right? So in this case, we can have a nucleophile or a base. Same thing over here, and a base. And we talked in the last video how substitution and elimination, which one prefers substitution? And let me do this in a different color. Substitution prefers nucleophiles, and elimination prefers bases, right? So, and that's what we're gonna do. Um, for this one, we can either do nucleophiles or base. So we can either have a substitution or an elimination. So it's gonna be tight over here, right? And then same thing over here. I should have just combined these, but too late. Or an elimination, right? So same thing. So this is where the fun stuff happens. You know, you can have multiple. This is a two-step reaction now, right? We can go from alcohol all the way back to either a nucleophile or a double bond, right? So that's we can get there from two steps. And kind of what's standing between your way is, don't forget about the nucleophiles and bases just because this is a new section, new chapter, right? It always applies. A reaction is a reaction, and we talk about substitution and elimination. So you guys should pay attention to that. Other than that, that's all the reactions for alcohols. Nothing too crazy. All makes sense. We've seen it before. Not nothing complicated or mind blowing or like doesn't make sense because all of these make sense, right? And this is a special one because it's OTS. If anything, this can throw you off because you don't see this a lot, the OTS. So, but think of it as just another halogen, right? TS, TS over here, tosylate. So, with that being said, let's get some practice in and see if we can apply these. So, alcohols. So, find, let's do naming first. Find IUPAC name and classify each of these alcohols. So we haven't seen this in a while, right? But again, you guys should be familiar with that. Okay. Ooh, and this one's a mixed one. And then um let's do this one. 2, which of these will react fastest? Fastest to HCl. OH. Okay, everything's in there. Okay, so take a second, pause the video, and come back with your answers. Okay, first, this one. What did you guys get? Find the IPAC. You guys should have gone um, 3 ethyl, 3 pentanol, right? And if you guys are wondering, you guys should have gone and drawing something like this, right? OH, that should have been your drawing. And that's CH3, CH2. There's 3 of those. They're what groups are they? Methyl ethyl groups, right? Ethyl groups, and that's what we have. 3 ethyl groups, 1, 2, 3. But um we need to find the longest chain either way. So 1, 2, 3, 4, 5. And then the origin of the third carbon, things like that. So nothing too crazy. And over here, and what is this OH? This OH should have been primary OH, right? I mean tertiary. So you should have gone tertiary OH. And for this one, we should have gone 3-methyl 4-pentan 1-all, right? 3-methyl 4-pentan 1-all. So again, this is what I was talking about. You need to know which are priority when you're making your parent chain, right? So we know OH is more prioritized than a double bond, so we're gonna number from here, right? 3 4, 5. And we said here our 4 pentane, right? Because it's pentane because of that double bond, right? The alkene. So it's in the fourth carbon, and then our alcohol is in the first carbon. So remember to always be as detailed as possible. We want to know where those things are, right? Okay. So which will react fastest to HCl? We said HCl will, will prefer what kind of reaction? It prefers SN1 or SN2, right? Um, so in this case, we look at, you know, what is what are the priorities, what are the classifications of each of these alcohols, right? This one's obviously a primary. Um, this one's secondary, tertiary, and secondary, right? So now, obviously, it's not going to be either of the secondaries, right? And this is where it gets interesting. Um, we know SN1 prefers primary, I mean tertiary, right? And then SN2 prefers tertiary. So why? Which one would you have? Would you choose based on that? You guys should have chosen the primary as the fastest, and then this one as the slowest because of that SN2 factor, right? SN2. So SN2 is prioritized over SN1, even though it can still go to the front side, but SN2 is more prioritized because you know if they were to say with a strong nucleophile, then for sure SN2, right? But between SN2 and SN1, SN2 is more prioritized than SN1, right? Okay. So with that being said, nothing too crazy. Naming is naming. You guys have seen a lot of naming. So let's go ahead and move on to our next functional group, right? Our next functional group is ethers, right? So ethers, we know they have what kind of general structure? ROR, right? ROR. And again, you kind of see here, they can be symmetrical. They can have the same R group, or they can have different R groups, right? Symmetrical or unsymmetrical. So there's no classifications to them, but for nomenclature, again, you could have the common, which is going to be, again, just ending with ether, right? And then you can have complex ethers, which you'll have to use oxy. So there's no IUPAC um, for these because you can't really do a long chain because, there's it just depends on the molecule. So let's see. And just more about ethers, you can have the reactions with it. This is the biggest one, Williamson ether synthesis, right? So that's probably the first official named reaction, right? Williamson ether synthesis, which is basically making an ether. And the biggest thing about this, and I'm gonna color this too, because you need an alkoxide oxide attack on less hindered Rx. So alkoxide attack on less hindered Rx. So what is that gonna look like? Think of it as an um, O minus, right? Oxygen minus on a primary Rx. So we know what primary looks like, right? And this is how you make an alkoxide, and this will kind of a summary of what you guys will see later in the question that I'll be giving you guys. So How do you make an alkoxide? Let's say we have CH3, CH2, O, H, right? Plus Na, H, minus, right? So these aren't together. And we don't want to forget the lone pairs. And then now, what's attacking what? We said, and this is not the alkoxide attack on the less hindered um, Rx, right? So we follow the electrons with our notation, right? And then this bond over here, this H, will go over there, thus making our O minus. O minus, right? And then Na plus H2, right? So this is what we want. This is the alkoxide that we want, right? Alkoxide. And now we can use that to attack less in their Rx to make ethers. And you kind of see here, this O right here, this is an R group and this is the O. So we just need to get rid of that Na and put another R group in there to make ROR or ether, right? So that's kind of what we're going for. So with that being said, to make ethers, you can also react with strong acids. So let me go on the next page. So ethers, you can also have reactions with strong acids. Strong acids take apart, right? So strong acids converted to good leaving groups, right? Good leaving group. So let's say we have an ROR, and let's say we have a strong acid, HBr or HI, and two equivalent. This one is actually gonna separate the ether. So, and you need two equivalents because you have two pairs over here, right? So you're gonna end up with either RX plus RX, right? So you just split these apart into two. So nothing too crazy. Oh, plus H2O, of course. Don't want to miss that. And here is kind of like an interesting fact about it. If it's a secondary or tertiary R groups, you're gonna go through SN1. If it's primary R groups, you're gonna go through SN2, right? So that just means if let's say we have a tert butyl or just a regular methyl group, right? Things like that. But it shouldn't be a big of a deal because since you're having this, it shouldn't matter if it's R or S. But either way, just a good info over here. Okay, so let's do practice and see what we get. Okay, so ethers, where am I? Ethers. Let's say first, let's do as always, find IUPAC name, or in this case, and then over here, so the IUPAC name is a complex name, right? Let's see. Oh, okay, let's do that. Two common name. Okay, so take a second, take a minute, pause the video, and come back with your answers. Okay, first, you should have gone something for S oxy octane, right? Oxy. So in this case, our longest chain isn't um isn't the ether, and it never really is, because yeah, it never really is because you don't go through the oxygen to go your longest chain, right? You just go straight through your longest chain. One, two, three, four, five, six, seven, eight. And once you do that, you just name your substituent. So this is an ethyl group, right? And it's an S-oxy octane, right? So that's really all there is to it. Yeah. Um, Nothing too crazy. As long as this is different from the common name, as you'll see, because the octane is not a common name. But over here, to find a common name, we just name both of these sides, right? And we know those names. We have a sec butyl, and then a methyl group, ether. And then you can do the same thing over here. We have an allyl group, and methyl again, ether. Right? That's all you need to do. Nothing too crazy. Common names and IUPAC names are pretty much the same. If you think about it, because you know, eth, ethyl, and then octane, but you have to again be as descriptive as possible. Where is that ethoxy? It's on the fourth carbon of the longest chain, right? So that's all there is to it. So same as all any of the other IPAC rules, right? So there's that. Now let's go to some of the reactions, and this is going to be a good one. These are going to be good questions. I think so. Ethers. So we're in three. So before we have room, which will provide the best yield by Williamson ether synthesis? So our choices are, and this time I'll give you choices because, obviously it's going to be impossible to do this. But, and the choices are actually make it harder. So A, bromobutane plus sodium meth oxide. B, oh, actually, hold on. Wrong, wrong, molecule. Okay, let me just surely but surely, slowly but surely, I'll erase this all. Okay, so it's actually bromobenzene. So bromoben, bromobenzene and sodium, and then here bromobenzene again, zine plus bromomethane, right? Plus C, we have phenol plus sodium methoxide, and D, we have sodium phenoxide plus bromoethane. Ethane. So pause the video, take a second, take a minute, and show me which you got. So you guys should have chosen the sodium phenoxide with bromoethane. So you guys should have gone with D. And why is that? We said Williamson ether synthesis wants or likes alkoxide attack unless hindered. RX, right? So that's what we know with Williamson ether synthesis. Alkoxide attack unless hindered RX. Well, this bromobenzene over here is what? Like this. So bromo group and then sodium methoxide, right? Like that. So this Br is what? A tertiary or a secondary, right? So possibly that's pretty less hindered. Um, so this one is also bromobenzene with a bromomethane. Bromobenzene over here again, and then plus a bromomethane. This one has no alkoxide, right? So that's a no. There's no alkoxides over there. What about this one? Phenol. Phenol, we know phenol looks like this, right? The OH, um, right? The OH, and then sodium methoxide. So something like this. So there's no alkyl halide on this one, right? Because it's an alcohol. It's an alkyl halide. So we can't do that one. But this one, sodium phenoxide, O, O, ONA, right? Sodium phenoxide plus bromoethane. So we have an alkoxide over here and a primary alkyl halide. So primary versus secondary. Primary will be the less hindered, right? So obviously that will be D. So things like that, you just have to think about it. You know, they they can present this in many questions, in many different questions. They can do the names, right? They can have it drawn for you, things like that. But as long as you know Williamson ether synthesis is an oxide attack on the less hindered, the better, right? So that's all there is to it. So let's do another one. These are fun. So, okay, let's do one more. Ethers, which cannot be prepared by Williamson ether synthesis, right? So let me give you A. Isopropyl methyl ether. B. Tert butyl methyl ether. C. Tert butyl phenyl ether. D. Tert butyl um ethyl ether. So pause the video, take a minute, and let's see what you got. So you're back. You guys should have gone C. And why is that? So this one you're kind of going backwards, right? So you got the products here, and now you kind of want to separate them. So isopropyl ether, methyl ether, right? Isopropyl group, right? Tert butyl methyl, tert butyl phenyl, right? And then tert butyl ethyl. So what do you know about those? If you cut them all in half, we have at least one um unhindered um group, right? One unhindered alkyl group. So we have the methyl group here that could be unhindered, methyl group over here, ethyl group is unhindered. But this one, this is all hindered, right? So this will cannot be prepared because we said alkoxide attack for Williamson ether synthesis is an alkoxide attack on the less hindered um, alkyl halide. This one doesn't have a less hindered alkyl halide if you break it up, right? So that's why it's this one. So two hindered for both. Two hindered. I don't have room for the ed, but okay, two hindered. So things like that. That's what you want to think about, and we kind of these are probably the hardest two questions you'll face with ethers ever. So you know, hopefully you guys understood that, and it's good practice, and it makes sense, right? And Williamson ether synthesis is the only way to make ether, period. So if you guys got that, you guys can make ethers in your sleep. So now let's go into epoxides. Epoxides are interesting. Um, you know, they're oxyranes, things like that. They're triangles, right? So they have 60-degree strain. They're also called oxyrane. Um, for naming is interesting for this one because it has three. For epox, oh, I don't know what I was trying to. Epoxy, alkane, U, number where oxygen attach, where it's attached, right? And then as an oxyrane, and we'll go over these all when we practice them. Oxyrane, you know, oxygen is numbered one, right? For an alkene, this is the weirdest one for me. Alkene oxide, right? Replace the oxygen with double bond and name and name oxide. So this is what the name would be. You name it regularly and then add oxide to the end. So pretty weird, right? Naming's pretty weird. Um, let's go to another page for the reactions, and these will all make more sense once we do practice, right? So epoxides again, and this time with the reactions. So synthesis, you know, we talked about the Williamson ether synthesis. Now we're talking about epoxide synthesis, right? So this is a version of Williamson ether synthesis. It's an intramolecular version of it. Molecular Williamson ether synthesis, right? On halohydrins. And halohydrins, we were introduced that a while back, right? So let's say we had something like this. That's over here. Things like that. Proton trans. We have a proton transfer, which is from the you know, the base, and then you end up with this. So this is where we're getting the halohydrogen and everything from, right? And then it closes, right? So this will go over to here, and then our halogen comes off, leaving it, and it's an SN2 process, leaving us with something like this. Okay, that O is pretty ugly, but you know, but then whatever, right? Things like that. So it closes up like that. So nothing too exciting, too crazy. That's kind of how it makes. We don't really, well, we focus more on breaking epoxides than making them, but making them is interesting, right? And this is the key word for epoxides, right? No other ethers or alcohols don't use it. Halohydrons. It all starts with halohydron, right? So, and this is the halohydron, right? We have the halogen over here and the hydrogen, which is the um, alcohol, right? Okay. Now let's go to another epoxide has a lot of reactions, right? So, and I think I can finish this in all on one page. Epoxides. We have, we said the opening, right? Epoxide opening. So with opening, it's going to be nucleophilic addition. Addition. It's two steps, and first it's going to be an SN2. So that's important, right? Backside attack, things like that. Um, and two, protonation, right? So to get that OH back, right? If you were thinking back to the synthesis, we end up with an oxide, so we just protonate it and get back to an OH, right? Okay, so that's that. There's also something called mesoepoxides, and that's, we know what meso compounds are. Mirror images on the same molecule, right? So mesoepoxides have two enantiomers, um, and it's 50-50, so it's racemic, right? 50-50, so racemic. And also we know it's achiral reactants. Okay, and now let's go with acidic opening. Same thing with ethers. We have acidic conditions, acidic reactions, things like that. So same thing with epoxides. Acidic opening, I guess. I guess we can name it that. So basically, it's going to be something that has a HZ, right? And again, nucleophilic. It has to be nucleophilic. And it's two steps as well. Two steps. Two steps, and the steps are kind of backwards. Protonation, because again, it's acidic, right? So we have a lot of protons. Protonation, and then SN1 instead of SN2, right? SN1. So nothing too crazy. Um, that's pretty much it. And I think it will be better with, again, examples. So let's say some examples. So offside. So let's name some stuff. So let's name these all different ways, I guess. Find the name. So the epoxy alkane, oxirane, alkane oxide. Find the names. Of this one, and I can have room, so might as well use this up and this one. So find the names, and so take a minute, pause the video, and give me all the names you come up with. So for this first one, you guys should have gone 1, 2, epoxy, 1, methyl, cyclopentane. So this is the epoxy alkane part, right? And also for this one, you should have gone 1, methyl, cyclohexene oxide. So this is the third one, the alkene oxide, right? When you convert this into um, a double bond, right? And okay, oh, I forgot the methyl group. You guys are probably calling me crazy. Okay, there should be a methyl group right there. So sorry about that. And On this one, there's no oxirane name, and that's because for this one, because it's a ring, right? So no oxirane, um, because it's attached to a ring and it's kind of just symmetrical, things like that. So sorry about the methyl group. So hopefully this all makes sense now. So let's go through this. One, two, epoxy, right? One, methyl cyclopentene. So for this first one, I'm gonna color this um, blue. We went this way. One, two, right? One, two, and then the epoxy is obviously this one, right? And then one methyl cyclopentane. And I think it's the same for the second one. One methyl cyclohexene oxide. So we numbered it the same way because now this is the double bond, right? So things like that. And let me just make this clear. One as well. So right there. Okay. So now let's do the next one, and this time let's color it right off the bat. So first one, you guys should have gone two two dimethyl oxyrane, right? Two dimethyl. So we numbered it again. Oxygen is one, right? For this one, one, two, two, three. So now, what other names did you guys come up with? Um, you guys should have gotten also two methyl propene oxide, right? So if you convert this into a double bond, we're just gonna end up with something like this, right? So we'll have one, two, three, one, two, three, right? And just to make that clear, we turned it into double bond, right? Okay, and then last one, you guys should have gotten one, two, epoxy, two, methyl propane, right? So this time, we don't number the oxygen first. This time we numbered from here. One, two, three. So that's how you go about that. So a lot of different names to name epoxides. Pretty fun. Gets a little bit tedious, gets annoying sometimes because you never know what they're asking. You kind of just have to gauge the answer choices, like which one of these is this molecule. So you kind of have just to gauge because all of these can be in the choice, right? So it can be one, it can be A, B, C, all of the above, right? Okay, so now let's switch gears to our reactions. So find a product as always. Find a product. CH3OH, H2SO4. So take a second, take a minute, pause the video, and come back with your answer. Let's do this triple. We haven't used this one. You guys should have gone, and obviously this is a ring opening, right? You guys should have gone this OCH3, oops, OH, right? And why is that? That is because it's gonna be a what? An acid, right? This is gonna be an acid. This is an acid, and we know acids go through SN1, and therefore, you know, attack from the more substituted. So it attacked over here, right? More substituted. But let's say if it was, let's do another color over here. Let's say if it was a nucleophile instead, right? Nucleophile, something nucleophile, whatever. Where would it attack? We know nucleophiles will attack um, opposite, right? We know it's an SN2, so obviously it's going to attack on the less substituted atom, so it's going to attack over here, right? So our product would have been slightly opposite H3, right? So that's what would have happened. Um, so things like that. So kind of pay attention to that. Nothing too complicated. The most complicated is, again, same thing with nucleophiles and bases. Nucleophiles is substitution, bases is elimination. This one, acid versus nucleophiles. Acid is SN1, nucleophiles is SN2, which makes sense because we know nucleophiles prefer SN2 anyways, like strong nucleophiles. So, and that depends on where it will open from, right? So, and kind of to just finish this off, um, you know, this the OH is up here for the green one, right? So this will go right here, right? And then vice versa for the purple one would have gone over here. So things like that, nothing too complicated. Again, pay attention to nucleophiles versus acid, right? What am I on? Purple. So pay attention to this and pay attention to nucleophiles, right? So that's it with epoxides. Nothing too crazy. Okay, now let's talk about hydride and alkyl shift. So what is it? Why does it happen? So this happens because of carbocations. So this is better known as carbocation rearrangement. So we've seen a couple of reactions that turn into carbocation intermediates, right? So basically, carbocations prefer the more substituted, right? They prefer tertiary over secondary over primary. So if they have a chance, if a carbocation, let's say, if a carbocation has a chance to jump into a more stable um, classification, it will. So right now, this is what is this? A secondary carbocation, but it can jump to over here, right? Carbocation, and now it's a tertiary. So that's what would it would prefer, right? And then we can even do um, primary one as well over here, right? So that's what would happen. So if you have a carbocation intermediate, look for possibilities of it rearranging. And that's important because if, let's say, we get this, you know, this is our intermediate, we know it can jump, right? That can jump. So our product would get added over here somewhere, right? But then again, it can jump again over here, right? And the thing with this is it can only jump to the adjacent, right? So it's not going to keep jumping all over the place like resonance type thing. It's just going to, let's say this is where the place our carbocation intermediate ends up. It can only jump up to here, right? And so on and so forth, just one at a time. Um, and actually, let's do a practice. And I think I can fit it over here. So, which is most susceptible to rearrangement? And this is a really big concept that a lot of students fall for because they forgot to rearrange that carbocation and they get the wrong placement of you know addition or substitution product, things like that. And this, you know, works with every reaction, as I said, that makes carbocation. So it's not just addition, substitution, elimination, or alcohols or epoxides. It's with any reaction. Okay, so take a second. Which one do you guys think will be more susceptible? You guys should have gotten this last one. Why? Because this one is already tertiary, right? So that's not going to leave because that's the most stable. This one is already tertiary as well, so that's not going to leave. This one's secondary, but if it jumps over here or over here, it's still secondary, right? So there's no point in jumping. But over here, secondary, and this is kind of the example I gave you, it can jump over here to tertiary, right? So that's more susceptible to rearrangement because we can get to a more stable carbocation form. And again, don't get confused by the hydrogen and alkyl shift. It's basically just carbocation rearrangement, right? And you can kind of tell that obviously if it's a carbocation over here, you're kind of there's an H over here, and you're kind of just swapping places, right? Things like that. And you can do it with methyl groups as well, but um, it's not as common, but it can happen. So watch out for that as well. So, like for example, this alkyl group will just move over here, and then the carbocation will be over here. But that doesn't really happen. Things like that. So, with that being said, that's all of part 9, and this is again our agenda. And hopefully you guys learned something. Hopefully that helped. There was a lot of reactions. Hopefully they made sense. And you know, thank you guys for watching till the end. And I hope to see you guys next video. Thank you guys.